So, good afternoon, ladies and gentlemen. It is a pleasure for me to welcome you here to the first Nečas seminar on continuum mechanics in this winter semester. And I am happy that I may welcome here Kolář from the Faculty of Nuclear Sciences and Physical Engineering of the Czech Technical University. He received a PhD at this faculty in 2018 and is now an assistant professor there. And he is also of many papers related to curvature-driven flow and dislocation dynamics. So we are looking forward to your lecture, and please take the floor.
Thank you very much, Peter. So, welcome everyone. I think for the beginning, because this is not only like my work today, what I'm going to talk about, this is like a group work. So not only myself, but my colleague Petr Pauš, Michal Beneš, and I think the biggest credit should go to Professor Jan Kratochvíl. Many of you know him. Unfortunately, it's been 6 years since he passed away, and like very big portion of this topic was heavily influenced on him, because basically most of us can consider ourselves as his students. So today I'm going to talk mostly about the dislocation dynamics and a little bit about the curve evolution problems. So because we are mainly like mathematicians, so let me briefly introduce what are we talking about or what we do. So if you look at these pictures like A, B, and C, these are the photos from transmission electron microscopy of some material samples which have been subject to some like strain test, something like this. And the dislocations in the materials, they are described as an irregularities or microstructure deformations in the crystalline structure. And what is interesting, they can considerably affect, even in microscopic scale, the properties of the materials. And we are discussing mostly like crystalline solid materials, like metals. What is known from the experiments is they typically evolved in so-called slip planes, which are like crystallographic planes given by particular crystal configuration. So the movement is not arbitrary, but in like planar type motion. And one of the approach how to model such defects is using curve approach, line approach, because these irregularities can be modeled as a moving curves. Sometimes, as I said, they mostly live in the slip planes, and mostly it is a planar motion. So sometimes it's not true, and they can change from one slip plane to the other, and it is called the cross slip. This is kind of 3D motion, and this is topic on which we were working together with Honza Kratochvíl before he passed away. So we already have some interesting results on the cross, mostly the modeling ones. So if you look back again at these TEM photos, there are different stages, different types of defects, and mostly you can identify such a dislocation as these lines, which are either like straight lines or like many lines accumulated. So there are many fundamental or even advanced effects which we can observe, and what we try to do is to mimic such a behavior on microscopic scale. So before I start, some brief introduction to the dislocation dynamics. So I made some efforts to prepare a historical overview, because this field of the material science, it's quite long, and it comes even to the beginning of the 20th century, to the 30s. So the origin dates to the beginning of the 20th century, and first theoretical concept was given by Vito Volterra, and he was studying at the beginning of the 20th century the singularities produced by plastic deformation. So first theoretical concept of the dislocation is mentioned more than 100 years ago. Then it was like systematized, and in 1930s, Taylor, Polanyi, and Orovan, which is like famous name in dislocation theory, proposed like serious physical theory that such a dislocation, such these microscopic irregularities may be actually responsible for the macroscopic deformation in the slides. And you can see they the dates of their papers were practically overlapping. So in the like 30s, 40s, it was mostly a mathematical theory. And right in the 1950s, the abstract theory became a reality, because in 1950s there appeared the technique of transmission electron microscopy, and the existence of dislocation was proven experimentally by the first observation in the 50s. So after the 50s, in the 20th century, they were developing an experimental method how to track their movement, how to measure the effect on the macroscopic scale, and so on and so on. And roughly speaking, after 90s, a broad range of models and computational techniques emerged together with like increasing computational power. So these days we have different kind of models which differs on spatial scale, on time scale, and in the recent years, like a hot topic is like multi-scale techniques which try to merge modeling in the different scales together. So when we speak about the scope of the modeling, I think this is like self-explanatory. Here you've got like space scale and time scale together. And on the macroscopic scale, we usually consider the techniques of continuum mechanics mostly applied to the crystal plasticity. And based on our space scale, we can consider either like polycrystals, single crystals, and all of these methods are basically like linear elasticity, finite volumes, finite elements, etc., etc. So very familiar to every one of us. On the other hand, on the opposite side of the space scale, we've got a so-called MD, which is like family of molecular dynamics methods. So really short time scales. And DDD, it is the abbreviation for dislocation dynamics, or more particularly discrete dislocation dynamics. It is somewhere between these two words. So the objective of this dislocation dynamics theory is somehow to fill the gap between the fully continuous models and between the atomistic models. And of course, you can see there is even here there is a quite wide range of the space scale. So more the right we are, like the more dislocations and more rough description we consider. So usually around this scale, when the microscale slowly is meeting the continuum mechanics methods, the people usually work with clusters of dislocation. They describe densities of dislocation in the crystal, and so on and so on. On the other hand, more closer to the nanoscale we are considering rather single or elementary dislocations, or a couple of dislocations, something like this, and we focus on modeling or description of like very fundamental mechanisms. So what we are trying to do with Michal Petr and Professor Kratochvíl, we are basically around such a line. So the objective of our study was the behavior of individual dislocations and how they interact one to another and how they are influenced by the external load. So we are probably somewhere like here as the red dot. So the literature on the topic, basically these days, many books are available. So for example, very classical books, Introduction to Dislocations, even at our faculty, the course on material science somehow like uses this book, which is about 50 years old, and more, some of them are very modern. Even the books dedicated purely to computational methods are available these days. So huge amount of literature is available. So now let's start with something like really equation-like. So basic overview, how we model the things. So as I already commented, in our descriptions, the dislocations are considered as the individual curves which move in their respective slip plane. So what we like postulate is such kind of geometric evolution equation, which roughly speaking says that normal velocity is proportional to the curvature, also known as the line tangent, plus the external forces. And the thing is, because this is kind of non-Newtonian motion type, because in like Newtonian motion type, we've got velocity is proportional to the acceleration is proposed to the force, but here we've got like velocity is proportional to the force, non-Newtonian style. So where does it come from? And we originate from one of the original paper of Honza Kratochvíl from 2008, when they proposed such kind of model with one of his colleagues. And the fact is, in the dislocation community, they are practically using such kind of non-Newtonian model, which says B stands for the physical parameter, drag coefficient, and the velocity is proportional to the sum of all the forces, including the dislocation self force, which is like responsible for straightening, trying to some energy minimization, and so on. However, in the model which was proposed by Honza Kratochvíl, they approximated the self force, which is quite a complicated stuff, by a curvature times a line tangent coefficient. So they came up with such a model, which is very similar, for example, in the models used in the image processing and like crystal growth and so on and so on. So some mathematical analogy. Here, as I commented, the B stands for the drag coefficient, T stands for the line tangent coefficients. So at the end, they approximated the motion of the dislocation by this diffusive motion of curves. And this is what we are working with. So far, we've got the effects which we already more or less successfully incorporated in our model. So first, maybe I will be commenting the line tension effects, which is kind of anisotropy and self-force effects. PSD channel, which I call the convenient boundary for the evolving dislocations. This is like restricted to the type of material which we are trying to simulate. Different loading regimes, topological changings of the dislocation because they can interact one to another, and like sophisticated things like merging or splitting can appear. Force interactions with multiple dislocations together in different slip planes. Interaction with some external sources like obstacles, precipitates, particles, and so on and so on. And finally, the effect of cross-slip, double cross-slip, and later the multiple cross-slip, which is the thing, as I commented, kind of 3D motion. So you can consider this one as like a brief overview what I'm going to talk about today. So very, very brief fundamentals of the dynamics of curves. Let's imagine such a curve gamma. It is our dislocations now, no matter if it's closed or open, but we consider it evolves in the plane and it evolves in the outer normal direction. The velocity depends on curvature and external forces. So maybe I'm going to like repeat familiar things to you, but we've got like two ways how to do such a how to describe such a motion. Direct description or the implicit one. So the implicit one, this is what actually I don't prefer so much because it's computationally quite demanding. As far as I know, Michal, for example, prefers very much the level set or phase field methods, mostly, but for crystal growth, for the other things. For dislocation dynamics, it is not so convenient because of the computational costs and other problems. But all of us practically know how we deal with the implicit description and implicit tracking of the interface. However, one advantage is the implicit description includes like out-of-the-box topological changes, which is a big plus. In the direct one, we've got to do it algorithmically. As you will see, it can be a little bit more problematic. So, speaking about the parametric description, I prefer this one because it's easy, fast, convenient, quite robust. And even if we consider more dislocations interacting one with another, it still allows us to develop quite a fast computational framework. So this is just a brief overview based on fundamentals of differential geometry. So we can, when we describe the dislocation directly by some parameterization, we easily formulate the tangent vector, the normal vector, from the Frenet formulas, the curvature, and at the end, we can prescribe this dislocation motion law, like normal velocity proportional to the curvature plus external force, as a system of two degenerate parabolic PDE. So this term, it stands for the curvature times the line tension. Here, the forces applied to the curve in the normal direction. And finally, the last term, something in the tangential direction, which is called a tangential redistribution. Why it is important and why it matters? Because below this one, I put in a box quite a sophisticated ODEs. So before that, maybe I show a picture. Why such a tangential term matters? This is actually one of the biggest drawbacks of the parametric method, because when we deal with it numerically, we can reach to a situation when the discretization points start to accumulate to some parts of the curve and be very sparse on the another one. And this is a problem with numerical stability. And also with this problem, when we consider, for example, topological changes or interaction of one dislocation with another, or interaction of the dislocation and precipitate. So what we want to achieve is like stable scheme, which saves some degrees of freedom. If we can prescribe this tangential term, like tangential velocity, accordingly or smartly, it can help us to redistribute the discretization points as we need. So for example, here you can see two dislocation curves sliding in some channel, and in the left one, you can see here the discretization points are distributed almost uniformly. This is what we usually want to achieve. On the other hand, if you look here at the right one, you can see they are not distributed uniformly because they are accumulated. If you track the red dot, they are accumulated in here, and they are basically the parts with the biggest curvature. On the other hand, we don't need so many discretization points to approximate a straight line. So few points are enough here and few points are enough here. Yes, it's pros and cons. And to control such a behavior, we can control it by smartly chosen term alpha tangential redistribution. So what we use is a model which originally comes from the idea of our colleagues Daniel Ševčovič from Slovakia and Professor Yazaki from Meiji University, and they proposed this driving redistribution term based on this redistribution shape functions. It takes into account the information about the curvature, and by the parameter epsilon, you can control the strength of such a redistribution. And the fundamental idea basically is they want to keep the constant ratio between the total length of the dislocation or the curve and the relative local length. achieve doing this, they can formulate like one ODE per curve. So it is a coupled system. Two equations, two degenerate parabolic equations for the dislocation movement, plus one ODE for this tangential term. And if we are lucky and if we choose the redistribution properly, we can, for example, achieve something like this. Okay, for the numerical point of view, I'm again citing Daniel Ševčovič, because after some time, I think the most convenient numerical scheme is based on the flowing finite volumes method, which is basically very similar to finite differences. It provides very easy, very robust computational scheme. And for the time integration, probably the most convenient is semi-implicit method and backward direct integration for the tangential term. So from the numerical point, it is not a big deal. The only significant problem actually is the stability of the numerical scheme, which helps tangential distribution. Okay, so now let me discuss maybe this fundamental dislocation mechanisms. And as I already commented, I'm going to start with the line tangent. So if I skip again back 3 slides before, we can see there is a term T times the curvature, and T times the curvature approximates the self-force generated by the dislocations. And in literature, we can find like second-order approximation of the line tension coefficients, which looks like this one, taking into account the dislocations H energy, which is a physical parameter. They can be obtained by measurements, Poisson's ratio, again, different for each parameter, and finally the angle between the dislocation tangent vector and so-called Burgers vector. I'm not going to speak about Burgers vector so much particularly. It is a vector related to direct crystallographic configuration. So for example, for the dislocations in copper or nickel, they have different Burgers vector than dislocations, for example, in iron and so on. Basically, Burgers vector is given parameter from the physicist. And here we can see red line versus the blue line, isotropic versus anisotropic case. So the effect of such a line tangent is basically straightening the dislocation line. First effect, which I'm going to talk about, is a multiplication. But in literature, it's called Frank-Reed source. And here, if you look at this photo of transmission electron microscopy, you can see like many centered dislocation loops, almost the circles, not exactly the circles, but further loop. And this is called the Frank-Reed source. It is experimentally observed mechanism how dislocations self-replicate. Because starting from some initial dislocations pinned between like 2 points, for example, some impurities with material precipitates, something like that, under the effect of constant load or some constant stress, the dislocations bows out under the effect of the curvature and the forces. Since it bows out, like this one, sooner or later, the parts of the dislocations meet one another, it merges, creates one open loop and one closed curve which continues bowing out. So this is like self-replicating mechanism which goes along as the material sample is under some loading. So here there are 3 like simulating snapshots right before the splitting, making the split. Here, right after the splitting, making one single dislocation loop and one loop with 2 fixed ends, which tries to bow out again. And the third stage, when the story continues. So this is like first, let's say, qualitative mechanism how the dislocation works. And what we tried quite recently was to mimic such a behavior not only in metals but in silicon crystal, because recently we found interesting paper, not cited so much, and actually quite old, so maybe like almost 30 years old paper, in which they reported such a mechanism even in silicon crystals. So they proposed another model, basically model proportional to the function of temperature and resolved shear stress. In such a model, they had very negligible curvature effects. So they were able to experimentally measure and observe the hexagonal structure of such a dislocation in silicon crystal. So recently I tried to apply our model, even if it's not suited to such a problem. I tried to like tune it a little bit and apply it to such a problem. Because there were some, let's say, heuristical criterion experimentally observed how the dislocation segments break and form hexagonal structure after reaching some critical length. So this is what our model actually produced. So I've got like 4 times 3, 12 stages. Again, here the dislocation is like bowing out, and you can see almost negligible effects of the curvature. And after reaching some minimal critical length, the topological changes appear, forming one closed loop which keeps expanding, and straight line which again keeps bowing until it reaches some total critical length when this crystallographic, 6-folding crystallographic structure continues. Okay, so it was Frank source, line tension, and now I'm going to speak very briefly about the third effect. And this is dislocation versus boundary interaction. Don't be misunderstood, because boundary interaction, I don't mean like boundary conditions, but in the physical context, it means something different. If you look at this TEM photos, you can see there are like thick black bands, and these black bands or black stripes, they are actually walls created by clusters of dislocations which are accumulated one to another. So their density is so high that even in TEM photos, it appears to be homogeneously black. So they create something like a channel structure. And what is interesting is the dynamics between such a walls of the channel. So you can see there are individual dislocations which are like sliding through a channel, or sliding one against another, or bowing out of the channel. So typically, when in dislocation community, the people investigate the behavior or want to like couple of individual dislocations, they use such a channel, they call it PSB channel, which stands for persistent slit band, as a convenient boundary, so their dislocations don't escape like to the environment. So as I commented, in reality, such a bands are formed by clusters of dislocations, and what we use in our model, because we focus mostly on modeling like face-centered cubic metals, we have found a very convenient way how to describe such a walls, even for a high amount of the applied stress. This looks like this one, creating a potential barrier which prevents the dislocation bow out through the walls. So this is like modeling description. This one is like TEM photos of the effect which we try to mimic. And when I spoke about the applied stress, right here, I think now it is a good time to elaborate what we mean by the applied stress. So for the first one, Basically, the applied stress is the only external effect which we consider in our model. So typically, when we've got some loading test or some strain test, something like that, we express the material sample to some external loading. And then, for example, in face-centered cubic, it is known we've got like 12 crystallographic families of the planes. So somehow the stress redistributes. And what is the result? Is the applied stress acting in the normal direction of the dislocations. And now we've got like two ways how to simulate. In literature, it's called either the stress control regime or the strain control regime. This stress control regime, it's very simple, and actually the dislocation community use it mostly when dealing with like massive number of dislocations, like clusters of dislocations, because it is easy and quite convenient. However, it doesn't describe the reality so well because it tends to like overestimate the real situation. What we try to do in like more precise modeling when individual dislocations comes into play is to prescribe the total strain, where the total strain can be approximated by the shear strain rate times the time, and we can decompose it into the elastic part, like here, plus the plastic deformation part. So this integral is actually responsible for the area slipped by the dislocations. And here, in this like computational picture, you can see the actual differences between the stress control regime and the strain control regime. So for example, here, the blue one is the stress control regime in certain configuration with some amount of megapascals, and this black line is the strain control. What we learned with Professor Kratochvíl when we were investigating such a behavior when developing our model is that these regimes approximately differ by like 10%, slightly more than 10%. So our good guess was the real situation could be somewhere in between these two regimes. So the applied stress. The message is for small amounts, for small number of dislocations, we try to express the applied stress like this one. For huge amount of dislocations, the community who deals with it typically uses uniform applied stress because it is very easy and very convenient for like parallel computing and so on. So if I'm not mistaken, now I'm going to speak about the fifth effect. This is interesting because force interaction between multiple dislocations one to another. So as I have already commented, our model is specifically tailored for face-centered cubic crystals, mostly like copper, nickel, and so on. And from physics, it is known in FCC crystals, there are totally 12 slip system families because like it's a high ductility materials. So the number of scenarios which can happen is quite restricted. So the message is not arbitrary geometrical configuration is possible, only like restricted number of configurations. Here we dealt with two, possibly more dislocation curves evolving in two slip planes which are parallel one to another. And what is known from the theory, we can express the interaction stress between the dislocations. It's quite sophisticated formula. And once we know the stress field from one dislocation acting to another, we can calculate the force caused by the stress field simply by a Peach-Kolář formula, which is probably the most famous formula from all the dislocation theory. Basically, it tells us once we know the stress tensor, we know everything because we take the stress tensor multiply it by a Burgers vector, which is given for specific configuration, times the tangent. And voila, we get a force which is acting on the dislocations. Interesting question, which was proposed by Honza Kratochvíl was, what is the necessary stress to form the stable structures? Because the stable structures, in other words, dipoles, are somehow important for the dislocation community, because this dipole formation, because this dipole formation is basically associated with the stress, with the strain hardening. So the amount of stress to create the dipoles or to break down the dipole configuration is somehow interesting for the community. So when I speak like breaking down the stable configuration, it is known as the passing stress. So basically here you can see the two very simple, very elementary scenarios. The left one, two dislocations, it is time evolution, so little by little. Black one, the red one, they are in parallel slip planes, sliding one against another. And since the applied stress plus the interaction is so high, they just escape one another. The more interesting thing is in here. Blue dislocation, black dislocation, they evolve one against another. And since the interaction force plus the force given by the applied stress, they are in kind of balance, so they form a stable structure. So this is what the physicists know under the term dipole, and they are interested what is the value of the stress in order to form such a dipoles. And basically it's kind of open problem, because there is like no general pattern how to track this one. We tried with Honza Kratochvíl to predict such a dipole formation for two dislocations, because there are some very nice experimental data from the German group from 2005, and they were able to produce very detailed and very particular measurements. So what we tried to tune our model and evaluate the passing stress in the face-centered cubic copper under two loading regimes. As I have spoken, stress control and the strain control. So just to remind in this one, with the uniform stress in the channel and with the applied stress calculated from the total shear strain and the plastic relaxation. So if you look here at the left figure, this is like our first idea, how we try to calculate it naively. So we tried basically trial or error approach. We made some computational setup, prescribed some amount of the applied stress, and let the dislocations evolve one after another and observe if they stop or not. So we are tracking down the rate, the time change of the slipped area. And once we were basically doing a bisection. So once we were found a stable configuration, we have just like specified by a few more iterations what is the approximate value of the stress in which the slipped area rate of the slipped area reaches zero. And that's how we found out this stopping value of the stress in order to make the dipoles, or the next one would be the passing stress. Even if our computations are very fast and very easy to perform, it's quite a challenging task, because it's basically stupid idea, just trial and error, and most of the time is wasted for unnecessary calculations. So what we tried was to do the idea, which was again proposed by these two German authors, proposing this one. And we were trying, doing the strain control regime, identify the value of passing stress together with the local maximum of what they could measure throughout the channel. And in order to neglect all the influences like precipitates, impurities, and so on, we were measuring such kind of force or such kind of stress right in the middle of the channel. And with the local maximum, we identified this kind of stopping stress according to the theory. So our result is for the same geometrical configuration, for the same material configuration, we found out this value of this passing stress differs approximately by 10%. And what was very satisfying, our calculations very nicely fitted to the data which are provided by these two guys. So this is how we can do in the symmetric one, but even if they had a huge data from transmission electron microscopy, it is super difficult to find some samples in which they have almost symmetrical data. So typical case is the configuration is non-symmetrical. And then what happens? Basically, we are lost. Because it is an open problem even now, even for two dislocations, for example, this one, which is bowing out of the walls of the channel and interacting with this one. By the way, they are again in the split planes which are parallel to one another. You cannot find any algorithmical way or deterministic way how to evaluate the passing stress unless you have some symmetry. Why? Because if you visualize the magnitude of the interaction stress, which is normalized, then you can see this one. Almost zero everywhere, some parts attracting, some parts like repulsive, and basically impossible to predict something analytically in such kind of geometrical setup. Another case is here, very similar case, but here at least it looks a little bit better because more long the PSB channel is, the bigger chance for the dislocation which bows out of the channel to create some symmetrical configuration like this. And here in this type of scenario, you can theoretically use some symmetry, you can consider the axis in the middle of the channel and so on. So basically, such comparison of experiments and calculation in this location world is possible only when you have very clear, very pure data. And for the people doing transmission electron microscopy, it is quite challenging to find such a data. So this is a big problem. So I'm slowly moving, I think, to one of the most interesting parts, I think the sixth one, and it is the interaction with obstacles. Because I'm not a physicist, so by the word obstacles, they typically imagine like precipitates, particles, impurities, whatever in the material, what does not belong there. So here, if you look at again the TEM photo, there are several scenarios. If you have an obstacle in the material and the dislocation curve in the same plane, basically the dislocation can cut through the obstacle, like for example a knife cuts through something, or the dislocation is stopped by the obstacle, and then it can form a loop around such a precipitate, which is called Orovan loop. And such Orovan loops are observed, for example, here and here, for example, in here. Basically, they are identified with thick white spots, because this is quite a low resolution. There are some experimental data in which it is like better seen. And as I was commenting, our direct approach is not so well suited for the interaction with obstacles because it involves topological changes and so on. Here, I honestly say the implicit one would be much better, but I think the trade-off for the computational cost is too much. So, having the direct description, we just have to think about algorithmically how to prescribe when a dislocation splits into the two parts, or what happens when two dislocations meet one another and merge two things, merging, splitting, and ideally it should work together. So it is like, and again, for merging and splitting, you need some geometrical parameters, and then once you have too many parameters in your method, it becomes computationally not so clear. So let's start with the interaction. I think for the beginning, look at the left figure. There is like one benchmark configuration, no channel, just two circles, this spot and this spot. There are some obstacles or maybe precipitates. Basically, these precipitates, they are modeled as circular obstacles, which exert repulsive stress, quite a high repulsive stress, 200 megapascals. And when dislocation is coming through them, what can happen? You can see here, the dislocation is so short, so it is practically blocked. The motion is practically blocked by the obstacle. So again, it reaches some stable geometrical configuration in which the radius of curvature basically is very similar. Well, the geometrical situation in which radius of curvature is balancing the force. So that's why it stops. On the other hand, if you look at this one, the dislocation is much longer. It has some space to go around the obstacle, like here in several stages, and finally split and making one closed loop around the obstacle, which attaches to the obstacle, and one free dislocation which continues bowing. So as I was commenting, such an algorithmical treatment is difficult regarding the parameters. That's what we try to verify quantitatively. So we took such an experimental setup of making one stopping dislocation and one Orban looping. And then we measured Hausdorff distances for different discretization. In the case here, the lower table is the case without any kinds of topological changes. So this was the case when the dislocation just cut through the obstacle. And in such a case, it was very nice. However, once we included the topological changes algorithm to our model based on some parameters, on some thresholding in which the dislocation just split into the another one, it breaks down the numerical convergence a lot, basically. There is still some numerical convergence, but it is pretty slow. So this is, I think, very interesting finding. We are still not completely satisfied by such topological changes algorithm, but currently this is the best what we have, unless we want to change to some implicit description, which is, according to me, a big trade-off. There is just qualitative one qualitative result which was done by my colleague Peter, and it is an interaction with cluster of obstacles. No matter how many obstacles, the good thing is once we've got topological changes included, we can very nicely scale the algorithm. So no matter how many obstacles we have, it still works very nice. and working even with the clusters of obstacles. So depending on their respective strength, I mean the repulsive strength, it can cut through them like this one, making one big orthogonal loop around the cluster, or a single orthogonal loop around the single dislocations. So this is kind of mimicking what could theoretically happens in the channel with more obstacles in the same slip plane as the dislocations. So this is the dislocations. And finally, now I'm slowly coming closer to the main effect of what I'm going to talk about. And this is the cross slip and the double cross slip. So far, everything what I have talked about was a planar case, except the case when they were two dislocations parallel one to another, but it was still a planar problem. Here, this cross slip, you can look at the right picture. Again, some EM photo of the cross slipping. Is it a mechanism which includes kind of 3D motion? So here you've got a family of crystallographic planes, and when certain conditions are met, the dislocation skips to something intermediate, which is called a cross-slip plane. This is called a cross-slip, and when certain conditions are met again, this is this stage D, it skips again to a slip plane parallel to the former one, but another. And this effect is called the double cross slip. The people know about it very long. It is experimentally observed. It is a well-known problem. And nowadays, it is still an open problem treated by many groups worldwide. And the funny thing, general agreement is it's thermally activated process. I'm going to talk about it by the end of my talk. With Michal and Petr, and mostly with Honza Kratochvíl, we worked under different assumptions, because Honza Kratochvíl was assuming from the beginning, or postulated from the beginning, this is not a thermally activated, but deterministic and stress control process under the assumption of low working temperatures. So under the assumption of low working temperatures, he was able to derive a deterministic criteria, which is purely stress comparison in primary plane, in the cross-slip plane, and based on such a stress comparison, the dislocation itself should decide if it changes the slip plane, or where, and even if. So this is the mechanism. And this mechanism can be activated by the different effects. One possibility you can see here, for example, one dislocation is sliding through the channel against another, and once the forces can balance, they can even, both of them, skip to a cross-slip plane, merge one to another, and form almost two straight dislocation lines. So this is what we don't consider now. I would like to consider a cross-slip which is activated by an interaction with obstacle, particularly with obstacle, because computationally it is much more interesting. And what the physicists know, it is also kind of frequent in a copper or nickel. So here, as you can see, the inequalities. This is actually what Honza Kratochvíl has in more than 10 years old paper with Petr and Michal. And this basically says they evaluate the applied stress and they evaluate the stress exerted on the dislocation by the obstacle, and they evaluate it both in the primary plane and in the cross-slip plane. And if the projection to the cross-slip plane is bigger than the projection to the primary plane, then the cross-slip occurs. If not, the dislocation continues happily in its own forward slip plane, under the assumption of quite a low working temperature. So this is a difference from the other. With Peter, my colleague, we were working on like a naive method, which is based on the tilting of the primary plane to the cross slip plane. So you can look in here. It is like side view. So the thick black line is the original primary plane, and then it is just tilted and then tilted again. It is pretty easy to rescale all the physical cross slip. However, here at the point A and here at the point B, it is actually not so clear what happens in the equation because there are some possible singularities. So it is unclear how it behaves, even if computationally it is very nice. So that's why we try to propose another method, not a tilting like this, but a vertical projection like this one. So here, if you look at the right one, you can see the difference. Here, there is a tilting, so we just tilt everything to one plane, and here, when we make a vertical projection, we just from up to down, we just map from up to down and again create a planar problem. And this one, if we regularize our cross slip by some smooth interface, we can overcome such a possible singularities. And this is our latest contribution, what we did, because doing this one, we tried to employ the geodesic description of curves. And our aim was basically to confirm the calculations by such a naive method are valid. So both of our approaches, they actually result in the problem of evolving curves in the plane, and both of our methods can produce comparable results. Even though you can see these two curves are a little bit different, they predict same like same occurrence of the cross slip, and that's what is important. So in what follows, I try to very briefly sketch the differences between these two methods. So first, let's get back to the origin of my talk. So this is what I consider velocity proportional to the curvature times line tangent, which is the self force, plus the external forces. And all the quantities are defined in the plane. Normal velocity, curvature, the force, physical parameters, unit tangent, unit normal, and so on. By the geodesic description, we postulated again normal velocity, but the normal velocity of the surface curve proportional to the line tangent times the geodesic curvature plus the external force. So now what differs is that instead of the original curvature, we assume the geodesic curvature, and instead of the planar unit normal vector, we just consider such a unit normal vector on the surface. Our original idea was actually copying one paper from Daniel Ševčovič and Professor Mikula, almost 20 years old paper in which they used such kind of description mostly for image processing problem. But we successfully adapted or tuned such a description even for dislocations. So here there are some mathematical similarities. So in the planar case, unit tangent and unit normal. In the surface case, unit tangent, unit normal. Quite difficult. In the planar case, we've got a curvature given by Frenet formulas. And in the surface case, we've got the geodesic curvature like this one. So for this one, we need at least twice the differentiable surface phi. we need to calculate Hessian and so on, blah, blah, blah. And finally, the normal velocity, just a change of the position projected to the normal direction. And here, the normal velocity is such as time change of the position projected to the normal direction. So we try to formulate everything by analogies. And here there is the comparison. The original planar model, system of two degenerate PDE, plus one equation for the tangential redistribution. And in the surface case, we've got again the system of two degenerate PDEs, however, with the different coefficients A, B, and C. So coefficients in front of the curvature, another coefficient which makes like a dragging along the surface, and the third coefficients in front of the force which is responsible for this vertical projection. This is how these models actually differ, and how we verified the models was on very simple computational setup. So our cross-slip effect was formed by one single obstacle, which was symmetrically placed inside the channel. So it was very naive, very primitive setup. Such an obstacle was like point source of some diffusive stress, which looks like this one. By the way, this 1 by r cube, it is very typical from the literature for FCC copper or for FCC, for precipitates in FCC metals. And this cross-slip criterion was evaluated directly at the tip of the dislocation in the middle of the channel. So we neglected the effects of almost everything, and we could formulate it as like 0D problem. So because of this symmetry, we could do analytical calculation and predict the occurrence of the first cross-slip and of the second cross-slip. And by the way, this angle delta between the primary plane and the cross-slip plane, it is again a given physical parameter, which is given by the particular crystallographic configuration. So it is not arbitrary, it is given by the physics. So this is what we were able to calculate, and then we tried to mimic such a behavior numerically and see what our two algorithms for the tilting method and the projection methods gave us. So we tried it for copper and nickel for 4 sets of like low working temperatures for which we were able to find the actual physical data in the literature. This is like the 4 stages on the cross-slip, close to the tip of dislocation, right between the cross-slipping. Now the evolution on the cross-slip plane, here there's what happens after it skips back to the primary plane again, after double cross-slip, and here some advanced stage of the evolution. And here, this is from the global scale. This is what you have already seen, and this is from the global scale, how the dislocation itself looks like. The blue dot, it is one point source of the obstacle. And here we can see how it like jumps to another slip plane and continues gliding. So when we were evaluating the occurrence of the first cross slip and of the second cross slip, in the case of the copper and in the case of the nickel for the 4 low working temperatures, here you can see again TPM, it means like tilting projection, and this VPM, it stands like for this vertical projection. So first cross slip, very comparable, second cross slip, very comparable for all 4 sets of the working temperatures, and again for nickel. So this shows like a very nice computational verification, at least for the people from the physical community, that our original and naive model based on the tilting produces at least not bad results. And this is what we are working on now. It's the effect called a multiple cross slip, which is basically a more computational demanding thing when the cross slip is forced not only by a single obstacle, but an array of obstacles ideally. some randomly distributed, and it is observed on some TEM photos. It can produce like pattern formation, like staircase patterning. Here it is from the side view, creating like staircase structure. So such a staircase structure can be very well observed, and this is what we are now trying to describe. So this is like very preliminary result, like in progressing. And to summarize my talk, as I was speaking about the cross-link as the stochastic process, we have made some comparison with probabilistic cross-link implementation, which is being like the standard in the dislocation community. So basically, they've got three conditions. They got the same condition as von Zakratochvil was assuming. Then they consider some minimal length of the segment of the dislocation must be fulfilled. And then the probability of the cross-link is under some exponential distribution, and basically it depends on the temperature, and these quantities are basically normalizing coefficient, some critical working volume, and all of this is related to particular crystallographic setting and particular metal. So the probability. And this is how we measured, together with Peter, the differences. One single precipitate inside the PSB channel, and given the applied stress. So here the x-axis was the distance of the tip of the dislocation in the middle of the channel from the precipitate. So the distance between the dislocation and precipitate. And on the y-axis, I apologize, it's quite a small font. It is actually a stress, a repulsive stress exerted by precipitate. So distance versus the stress. And the black region, it is actually the zone configuration of the distance versus the stress in which the cross-slip never happens. The yellow one, this is the zone in which the deterministic cross-slip happens. And here you can see the violet one, the purple one, and this is like a very thin zone in which the probabilistic cross-slip happens. Actually, the probabilistic cross-slip happens in all of this yellow zone and this violet zone. So we can see for some configuration, it is almost overlapping, for sometimes not. So this is, for example, the setup for 35 megapascals. And here there is again the left one, the deterministic cross-slip. And here there is probabilistic cross-slip. The yellow one, it is probability 100%. And the violet one is like the probability between 0 and 1. And the black one is like 0 probability. So again, very comparable. And the bigger the applied stress, the bigger differences they are, like this. The basic message is for lower stresses, for lower applied stresses, the probabilistic and the deterministic description is kind of comparable. And we try to summarize our calculation in such kind of stress map. So here on the x-axis, there is the applied stress from like 0 to 50 megapascals. And on the y-axis, on the y-axis, there is the obstacle stress, repulsive obstacle stress, and the black one, no cross-slip happening at all, even with the probabilistic or the deterministic description. Yellow one, both of the method produces 100% probability for the cross-slip. And the interesting thing is the red part. In the red part, the probabilistic cross-slip happens only and 0 chance for deterministic one, and the vice versa, violet one, is only our method, the deterministic cross-slip, and is capped to 0 probability for the probabilistic one. So we can see in some sense, the probabilistic cross-slip serves like upper estimate, and the deterministic cross-slip serves like lower estimate. And the reality is expected to be somewhere in between. So I think time is already gone for me. So just very few concluding remarks. I tried to speak a little about the methods, what we have, based on the finite volumes, numerically and analytically based on the curve dynamics. I tried to cover the fundamental mechanisms involving the interaction of like one dislocations with another and with the obstacles. And mostly I tried to describe our current working on the cross-slip effect related to the geometry, and also to the different kind of methods based on the tilting and the projection. For the small stresses, as I commented, the probabilistic approach, it seems to overestimate the deterministic cross-slip, so that's with upper estimate, lower estimate. And for the higher stresses, again, it appears from our calculations that there are, let's say, in some sense, almost comparable outputs. So latest topic, what we are working on is now, unfortunately, without Professor Kratochvíl, and this is related to the multiple instances of the cross-slip, making some patterning formation and creating a staircase structure. So we see how far can we go. So thank you very much.